Hello, everybody. This is Mostafa Jouybari. My talk is about turbulence behavior in supersonic channel flows with 2 and 3-dimensional sinusoidal roughness. This project is done under supervision of Professors Yuan, Jaberi, and Brereton in the Department of Mechanical Engineering at Michigan State University. Surface roughness can emerge as either isolated roughness like steps, joints, gaps, or a distributed roughness like screw threads, surface finishing, and ablation. Roughness is important to understand the physics related to the early transition to turbulence, heat transfer, and flight control. For example, this figure shows the underneath of a space shuttle. As you can see, the silica tiles, which are used as thermal coatings, introduce surface roughness that can alter the aerodynamic behavior of the vehicle, especially in the re-entry region. Existing numerical methods simulate either isolated roughness or simple geometry distributed roughness like wavy walls. They mostly use body-fitted conformal mesh to this end. Complex geometries such as realistic roughness geometries introduce new challenges in mesh generation and numerical stability. Even existing immersed boundary methods, such as Gauss-Cell methods, show some difficulties in dealing with complex geometries. Some of these difficulties are explained in the study conducted by Liu et al. We would like to propose a level set-based immersed boundary method to simulate supersonic flows over complex roughness geometries. Our proposed immersed boundary method uses a level set field phi, and it is defined such that phi equals to 0 corresponds to the solid cells, phi equals to 1 corresponds to the fluid cells, and phi between 0 and 1 corresponds to the interface cells. To impose a boundary condition, we first solve for the entire domain, then we correct for the boundary values. For example, to impose the Dirichlet boundary condition, we can use this relation. For test variable theta, the corrected, if we are in the solid domain, phi equals to 0, and the corrected value of theta gets the value of theta at boundary, which is called theta b. But if we are in the fluid domain, phi equals to 1, and the corrected value of theta gets the original value of theta computed from the numerical solver. Similarly, we can impose the Newman's boundary condition using this relation and employing one-sided differentiation schemes to calculate different differential terms here. For the purpose of this study, direct numerical simulations of fully developed periodic channel flows over two-dimensional surfaces, case C1 and C2, and two three-dimensional surfaces, case C3 and C4 are performed. All these surfaces share the same roughness crest height, but they differ in the streamwise and span-wise wavelength. The Reynolds bulk of the simulation is said to be 3,000. It is based on the bulk velocity and bulk density. And the Mach number based on the bulk velocity and the speed of sound at walls is said to be 1.5. We've used no slip boundary condition for velocity components and isothermal walls for temperature. The top walls are considered to be smooth, and the comparable Navier-Stokes equations are solved using a combination of monotonicity preserving and a compact schemes. To validate the immersed boundary method, case C1 is simulated twice, one with the immersed boundary method and one with a body-fitted conformal mesh. And the top figure shows the contour of level set for the immersed boundary method simulation, and the bottom figure shows the curvilinear grid for the conformal mesh simulation. And this figure compares different mean flow and turbulence variables between the simulation with the immersed boundary method and the simulation with the conformal mesh. As you can see, for all these figures, the results of the immersed boundary method, which are shown by solid lines, match perfectly with the results of the conformal mesh simulation, which are shown by dashed lines. And this validates our immersed boundary method. I've also produced an instantaneous flow visualization using the immersed boundary method simulations, and the movie is uploaded in my YouTube channel. The link to the movie is also shared in the supplementary material for this talk. These figures compare different mean flow and turbulence variables between these four surfaces, and the table compares the drag coefficient. As you can see, the drag coefficient is higher for 2D cases compared to the 3D surfaces, and this is consistent with the incompressible flows over these surfaces. Figure C shows the temperature, the mean temperature profile between and the mean temperature profile of these cases. As you can see, they obey the same trend as the drag coefficient. That is, the mean temperature profiles are higher for 2D surfaces compared to the 3D surfaces. The reason behind this is because of the associated shock patterns. This figure shows the contours of instantaneous divergence of velocity. As you can see, for 2D surfaces, um, we see strong shock patterns that have the same wavelengths of the surface roughness, and they go all the way up and hit the top wall and are reflected back to the domain. But these shock patterns are destroyed in 3D surfaces because of the surface roughness and are replaced by weak shocklets. These strong shock patterns impart in 2D surfaces impart a considerable amount of irreversible heat generation, and that's because that's why the temperature profiles are higher for 2D cases compared to the 3D surfaces. We've also analyzed transport of different components of Reynolds stress tensor, as well as turbulence kinetic energy, and they are fully explained in the supplementary material. Here, I focus on the stream-wise shear production term in the TKE budget P11. As you can see, for 2D surfaces, we see localized augmentations of P11 on top walls, and the location of these augmentations correspond to the reflection point of a shock wave, which is resulted from the surface roughness and is reflected back to the domain from the top walls. Another effect is that the reflected shock waves goes back to the domain and impinges another shock waves from the surface roughness and causes intensified shear production near the surface roughness. These two trends are visible for 2D surfaces, case C1 and C2, but they are absent for 3D surfaces, case C3 and C4, and the reason is the shock patterns are destroyed for these three-dimensional surfaces, and therefore we are not seeing any obvious localized shear production for them. In conclusion, a new immerse boundary method is proposed to simulate compressible flows over complex roughness geometries. Supersonic turbulent channel flows over two two-dimensional and two three-dimensional rough walls are simulated at Mach 1.5 and Reynolds bulk of 3000, and the results are compared. Our results reveal a strong dependence of mean flow and turbulence on the surface geometries and the associated shock patterns. And the impingement of the shock waves, which are resulted from the surface roughness, causes localized augmentations of turbulence production at the top walls. The locations of these localized augmentations showed the same wavelengths as the surface roughness for 2D cases. The future work will include analysis of more complex roughness geometries, such as sand grains. Thank you.